Hello. Okay, some solutions to questions 1 and 2. Shouldn't take too long, hopefully, and I won't make any mistakes. Good. Right. Here's the question. Summary question. That's the volume, fixed volume, and it has a safety valve. Let's draw some sort of picture. Let's get some sort of images up for you. There we go. Can you see? So we've got something with a box of gas with a safety valve. Okay. It's got a volume of 0.024 meters cubed, and it can safely, the pressure can be safely go up to 125 kilopascals before this valve lets all the air out or the gas out. Okay, so the question is, we're trying to find out the maximum number of moles that it can use. So because it's moles, we're using PV equals nRT. Okay. Let's have a look. We want to make moles the subject. So N is equal to, let's get this the right way around now, PV over RT. Okay. Now what do we know? We know V. We know the pressure because it can hold up to 125, and we're finding that just that maximum pressure. So we know the pressure. Do we know R? Yes, it's 8.31. Do we know the temperature? Does it tell us the temperature? 50 degrees. Okay, but that's cool. Our temperature is 50 degrees C. Don't fall into the trap. That's going to be 323 Kelvin. Just added 273 to it. So put the sums in, and it is equal to pressure 125 times 10 to the 3 times by the volume, which is 0.024, all divided by R. Remember, R is 8.31, the universal gas constant, times by the temperature is 323, equals. Okay, let's get the calculators out. And I'm going to calculate the top line first. The common error that students make, let's put this in first, 0, 2, 4, equals. If they try and do it all on their calculator at once, don't do that. It leads to mistakes. So I've done the top line. I'm going to do the bottom line now. Times by 323 equals, and the bottom line equals this number, 2684.13. Then I'm going to do that calculation, 3000 divided by 2684.13 equals, my final answer is 1.117 blah 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 1.1 moles. Okay, easy question. Students make mistakes. They get this bit right. They get this bit right when they write it down, and then they make the mistake of trying to do all of this on the calculator at once. Don't do it. You will make mistakes. Do the top row, do the bottom row. Well, we've got multipliers there. Okay, what's the next bit? Next bit, the pressure in the cylinder when the gas is 10. Okay, so now we know how many moles we've got because we've just worked it out. We are looking for the pressure when the gas is at 10 degrees C. So the temperature is 10 degrees C, which is 283 Kelvin. Okay, and PV, write your formula, nRT, make P the subject, P equals nRT over V. Substitute the numbers, 1.1 moles times by the gas constant, 8.31, times by the temperature, 283, divided by the volume, and the volume is 0.024. We'll get there. Now this time, 1.1 times 8.31 times by 283 equals, I'm not going to bother writing this out again like I did before because I've only got one divisor on the bottom there. There's not a multiple. So that gives me that, and then equals, divide the answer by 0, equals, and I get an answer of, looks like this, 107787.625 pascals. Okay, let's get rid of all this rubbish. Let's call it 108 kilopascals. kilopascals. Job done. Okay. Okay, next question. We have an electrolysis experiment where they've got some gas collected and they're asking us some questions about that. Awesome. Right, let's have a look. Let's move this a little bit smaller so I can read the question as we're doing it. Because I haven't the question. There we go, that's better. What does it say? Let's write down some data. We've got a volume of gas that we've collected. Let's write this down. The volume of gas collected was 2.2 times 10 to the minus 5 meters cubed. A little bit of gas. We know the collection pressure. We know it's collected at a pressure of 103 kilopascals. We also know that the temperature was 20 degrees C, which is 293 Kelvin. Don't fall in the trap. Calculate the number of moles. So we wanted to know what N is. Okay. Step 1. Write your formula. PV equals nRT. Rearrange to make N the subject. N is equal to, let's get this the right way around now, PV over RT into an R. Substitute our numbers in. We have 103 times 10 to the power 3. That's pressure. Times by the volume, which was 2.2 times 10 to the minus 5. Do you notice I'm crossing these little values up as I do them? All divided by the gas constant, which is 8.31, and then multiplied by the temperature, 293 Kelvin, which equals. Now, once again, I've got multipliers on the bottom there, so I'm going to do one row at a time. Okay. It'll save me making mistakes. And it takes a little bit of extra time to plug the numbers in, but it makes sense. 2.266. And then the bottom line is going to be 8.31 times by 293 equals 2434.83. Let's do my calculation now. 2.266 divided by 234.83 equals, and I get an answer of 9.3 times 10 to the minus 4, and what we're looking for, moles. Okay, and that is the answer that Mark Scheme told me, so that's all good. The next bit, the volume of this gas at 0 degrees and 101 kilopascals. Okay. So we've actually got to carry this forward now to our next bit. This time, what do we know? We know that the temperature is 0 degrees C, which is 273 Kelvin. Okay. We know that the pressure this time is 101 times 10 to the 3. So let's have a look. What are we actually trying to find? The volume. Write our formula. PV equals nRT. Rearrange. Volume is nRT over pressure. Substitute. 9.3 times 10 to the minus 4 moles. So let's think that way. Multiplied by 8.31, our old friend, the gas constant, multiplied by the temperature, 273, all divided by the pressure, which is 101 kilopascals. Okay, let's do this. Let's do this. 9.3 times by our friend, the gas constant, times by the temperature, that equals that. Divide that by the bottom line. Equals. And I get an answer of 2.088. The 2.1 times 10 to the minus 5 meters cubed. And that is my volume. Does that make sense? Does it make sense? It makes sense to me. Oh, sorry, can you not see that? So just to recap that one, that when the temperature was 20 degrees C, the volume was 2.2 times 10 to the minus 5. When we cooled it down to 0 degrees C, we've just calculated it comes out to be 2.1 times 10 to the minus 5. See how does it make sense that the volume's decreased because it's cooled down, you see, right? So, right, sort of ballpark figure, double checking our stuff there. So, enjoy.